This is lecture 7 of our differential equations course. We finished talking about second and higher order linear equations, and now we move on to chapter 4, which is about the Laplace transform. Before I begin, let me remind you one more time, the midterm exam is on Wednesday. Let's start with a little bit of revision. Recall that if I write an integral between some number a and infinity, then what I really mean is the limit as a variable r tends to infinity of the integral up to r. So, for example, c is a non-zero constant, then we can calculate the integral from 0 to infinity of e to the ct dt. And this really means the limit as r tends to infinity of the integral up to r. Or the limit as r tends to infinity of 1 over c e to the power ct, calculated at r and 0. And if c is a positive number, this is infinity. If c is a negative number, then e to the power cr tends to 0, and we just get minus 1 multiplied by 1 over c. Another example. Let's suppose we want to integrate from 1 to infinity the function 1 over t. And what this really means is the limit as r tends to infinity of the integral from 1 to r, 1 over t dt. Or the limit as r tends to infinity of the natural logarithm of t, calculated at r and at 1. Because we have positive numbers, we don't need to worry about the absolute value of t. So that's the limit as r tends to infinity of the limit log of r minus log of 1, which is 0, or infinity. In this chapter, we're going to be talking about piecewise continuous functions. What is a piecewise continuous function? It's a function which looks like something like the one that I've drawn here. This function is not continuous, but it's made up of 4 pieces, and each one of these pieces is continuous itself. To be more precise, a function f defined on the closed interval from alpha to beta is piecewise continuous on that closed interval if and only if there exists a finite partition of this closed interval, let's say t0, t1, t2, t3, t4, etc., where 2 rules are satisfied. On each one of these pieces, the function f is continuous, and at the end of each one of these pieces, all of the one-sided limits exist and are finite. Now we're ready to start talking about the Laplace transform, named after a French mathematician called Pierre-Simon Laplace. The idea goes like this. What does derivative do to a function? Derivative changes a function into a new function. The function that we start with we call f of t, say, and then after we've done the derivative of this, we find a new function which we typically call f prime of t. The Laplace transform is another way to change a function into a new function. Again, let's suppose we start with the function small f of t. After we've done the Laplace transform, this changes it into a new function. And for the new function, we're going to use a capital letter. And typically, we're going to change the independent variable from t to s. So let's do the definition. First of all, I need to be careful because this is only for inverted commas nice functions. Don't worry too much about these. We have a piecewise continuous function which doesn't get too big, basically this says. Then the Laplace transform of small f is a new function called capital F, which is given by this formula. It's the integral from 0 to infinity, e to the power minus st, small f of t dt. And we can either write this as capital F, or we can write this as curly L of f. When I'm using a pen, I would write this curly L like this. Do your best to imitate this. Just make sure that your curly L doesn't look like your ordinary L's. And the definition tells us that this new function exists for s greater than a, where a comes from this bound which says the function doesn't get too big. Let's do some examples. We'll start with the simplest function, the function 1. I want to calculate the Laplace transform of 1. I have my formula at the top. I'm going to replace the function f by 1. I'm going to be putting a 1 just here. So in other words, we have the integral from 0 to infinity, e to the power minus st 1 dt. And what does an integral to infinity mean? It really means limit. I'm skipping some of the steps here. This is the limit as r tends to infinity of minus e to the power minus st divided by s, calculated at 0 and r. Again, I'm skipping some of the steps. You can fill this in. This is equal to 1 over s. And this is defined as long as s is strictly positive. Another one. The Laplace transform of e to the power at. We can take our function e to the power at and we substitute this into the definition. So we're doing the integral from 0 to infinity, e to the power minus st, e to the power at dt. I'm not doing all of the details here. I'll leave this for you to double check. Fill in the details here. That's the integral from 0 to infinity, e to the power minus s minus a t dt, or 1 over s minus a, which is defined as long as s is strictly greater than a. Let's do another one. Let's suppose we have a function like this. My function is defined. My graph is slightly wrong here. I'll have to fix this. This shouldn't be here. This dot should be just here. It doesn't matter. Let's suppose we have a function which is defined to be equal to 1 if t is between 0 and 1. The function is equal to k if t is equal to 1. And the function is equal to 0 if t is strictly greater than 1. Calculate the Laplace transform of this function. We want the integral from 0 to infinity, e to the power minus st f of t dt. Now we have two functions. The function is equal to 1 between 0 and 1, and the function is equal to 0 after 1. If I put 0 into the integral, then the whole integral is just 0. So really, we're just doing the integral from 0 to 1, e to the power minus st 1 dt. And after we've completed the calculation, we find that this is equal to 1 minus e to the power minus s divided by s. And this is defined for s greater than 1. Next, sine 80. Find the Laplace transform of sine 80. This time we're going to need to do integration by parts. I'm going to be using the formula integral of uv prime is equal to uv minus the integral of u prime v. So we take our definition, which I've written at the top, and we replace the function by sine. We want to calculate the integral from 0 to infinity, e to the power minus st sine 80 dt. And of course, anytime we have an integral up to infinity, what it really means is the limit as r tends to infinity, and then integral from 0 to r. Now we have two functions here, a green function and an orange function. The green function I'm going to be calling u, and this orange function will be the v prime. What do we get when we do integration by parts? We get uv. So the green function is going to stay the same, and then the orange function will be integrated. The integral of sine is minus cos. So we're going to get minus e to the power minus st minus cos here. And then in the second bracket, we differentiate the green function to get minus s e to the power minus st. And then we integrate the orange function. The integral of sine is minus cos. Two minuses cancel out, and we just have one minus left. So that's the same as 1 over a minus s over a, integral from 0 to infinity, e to the power minus st cos 80 dt. Okay, still we have an integral with two functions multiplied together. So we use integration by parts a second time. Let me recap. First of all, we found that the function we're trying to calculate is 1 over a minus s over a integral of e to the power minus st cos 80. And I want to use integration a second time on this integral. And I'll leave this for you to check. I'm not going to do the details here. You can check that if we do integration by parts on this integral, we get another s over a, and then we get integral of e to the power minus st sine 80. But this is what we started with. This is just g of s. So we found that g of s is equal to 1 over a minus s squared over a squared g of s. We can solve this with g of s. And we find that g of s, or the Laplace transform of sine 80, is just a divided by s squared plus a squared. I'll leave this for you to double check. We could use the same method to calculate the Laplace transform of cos 80. And this time, we would get s divided by s squared plus a squared. I'll leave this for you to check. use the same method that I used in the previous example. You can write down a proof of this formula. Or we could use the same method for sine 80. And we would get a over s squared minus a squared. For sine, it was plus on the bottom. For sine, it's minus on the bottom. Why is that true? Because if we differentiate sine 2 times, we get minus sine. But if we differentiate sine 2 times, we get plus sine. So that's the only difference in the calculation, and that would give us a minus instead of a plus here. For cosh, we could do the same thing. Again, I'm leaving this for you to do. We'll get s divided by s squared minus a squared. The Laplace transform is a linear operator. In other words, the Laplace transform C1 F1 plus C2 F2 is just C1 Laplace transform F1 plus C2 Laplace transform F2. We're going to be using this fact later. I don't want to dwell on it. I leave the proof of this for you to write. So let's suppose small h is 5 e to the power minus 2t minus 3 sine 4t. Calculate the Laplace transform of this function. We're going to use the theorem to break it up into easier functions. This is the same as 5 multiplied by the Laplace transform of e to the power minus 2t minus 3 times the Laplace transform of sine 4t. We know the Laplace transform of e to the power 80, and we know the Laplace transform of sine 80. We can just put the formula in straight away. And then simplify a little bit. We get our answer 5 over s plus 2 minus 12 over s squared plus 16. We also have an inverse Laplace transform. And the way it works is, if capital F is the Laplace transform of small f, then small f is the inverse Laplace transform of capital F. Just goes backwards, just undoes or inverses the Laplace transform. So, for example, the Laplace transform of 1 is 1 over s, and the inverse Laplace transform of 1 over s is equal to 1. The inverse Laplace transform is also a linear operator, which, again, I leave this for you to check. For example, find the inverse Laplace transform of 10 divided by s squared minus 25. Now remember, we know that the Laplace transform of sine 80 is a divided by s squared minus a squared. And that sort of looks like what we have. We have s squared minus 5 squared. But we don't have 5 on the top, we have 10 on the top. We just do a quick rearrange, take the factor of 2 out so that we do have 5 divided by s squared minus 25, or 2 times sine 5t. Find the inverse Laplace transform of 1 over s plus 1 over s minus 2. Let me remind you of two formulae which we've done already. The Laplace transform of 1 is 1 over s, and the Laplace transform of e to the power at is 1 over s minus a. These are the formulae that we want. Because we can write down that the inverse Laplace transform of our function, because the inverse Laplace transform is a linear operator, this is just the inverse Laplace transform of 1 over s plus the inverse Laplace transform of 1 over s minus 2. And that's just 1 plus e to the power 2t. There's a theorem which says the Laplace transform of t to the power n multiplied by f of t is equal to minus 1 to the power n multiplied by the nth derivative of capital F. This is an important formula, so I want to prove this. And first, I'm going to prove it if n is equal to 1. N is equal to 1. It's just minus multiplied by df ds is equal to the Laplace transform of t multiplied by f of t. Now, minus df ds, that's minus dds of, this is just the definition of capital F, the definition of the Laplace transform of small f. And let's just suppose that we're allowed to take derivative inside the integral. In this course, I'm not going to worry about defining the details of when this is allowed and when this is not allowed. There's only one s in the integrand, it's e to the power minus st. So this is all we need to differentiate. The derivative of e to the power minus st is minus t e to the power minus st. Rearrange slightly. That's the integral from 0 to infinity, e to the power minus st. And then I'm grouping t, f, t together. But what is this? This is just the Laplace transform of t, f of t. So that proves that the formula is also true. That proves that the formula is true for n equal to 1. What about for higher n? If we use this formula 2 times, it's possible to show that the formula is also true for n equal to 2. And then we can show that it's true for n equal to 3, and then for n equal to 4, and so on. Now let's use it. I want to calculate the Laplace transform of t squared cosh 2t. I'm going to be using the formula that we've just proved. And let me remind you, the Laplace transform of cosh at is s over s squared minus a squared. So first, using the formula, we have n equal to 2. So minus 1 squared, d squared ds squared of the Laplace transform of cosh 2t. Or just 2 derivatives of s over s squared minus 2 squared. And I leave this for you to finish. I'm not going to spend my time doing 2 derivatives of a simple rational function like this. I'll leave this for you to check is 2s, s squared plus 12 over s squared minus 4 cubed. What about t to the power n? We can also use this formula for calculating the Laplace transform of t to the power n. Because t to the power n is just t to the power n multiplied by the function 1. What is the Laplace transform of 1? The Laplace transform of 1, remember, is just 1 over s. Using the formula, we have minus 1 to the power n multiplied by the nth derivative of the Laplace transform 1, or the nth derivative of 1 over s. That's minus 1 to the power n, minus 1 to the power n. Those are going to cancel out. N factorial over s to the power n plus 1. We just get n factorial divided by s to the power n plus 1. Now, if you look in the course material section, course content, whatever it's called, course material it's called, you will see an item called elementary Laplace transforms. You'll also find the page looking like this in the lecture notes. I recommend you have a table like this by your side during the exams. If we were doing a classroom course and I was setting exams in a classroom, I would still be giving this table to you. Let's go through it. The Laplace transform 1 is 1 over s. We've done that. The Laplace transform e to the power at, we did this. That's 1 over s minus a. We've just done the Laplace transform t to the power n, and we just shown that it's n factorial over s to the power n plus 1. I've also proved that the Laplace transform for sine at is a over s squared plus a squared. The next three, cos, sine, and cosh, I told you that you should do. What's next in the table? E to the at sine bt and e to the at cos bt. We've not done these yet. T to the power n, e to the power at. Well, we could use the formula that we've done to find this. U subscript c, we will talk about this next week, next Thursday. These two we'll also talk about next week. This one will come in 2 weeks' time. And then the final one we've just done. T to the power n, f of t. Take the Laplace transform, we get minus 1 to the power n, nth derivative of capital F. Now, let's do an example. Find the inverse Laplace transform of the natural logarithm of 1 plus 1 over s squared. Again, we're going to use this formula. We're going to use that the Laplace transform t to the power n, f of t, is equal to minus 1 to the power n, nth derivative of capital F. We're going to use this with n equal to 1. And then we're going to take the inverse Laplace transform of both sides. We're going to be doing t multiplied by f of t is minus the inverse Laplace transform of the derivative of capital F. So we're going to take capital F, we're going to differentiate it, then we're going to calculate the inverse Laplace transform, multiply by minus 1, and then divide by t. So let's do that. We're starting with capital F is the natural logarithm of 1 plus 1 over s squared, And I want to start by differentiating this. I get minus 2 over s cubed divided by 1 plus 1 over s squared by the chain rule. Then I want to calculate the inverse Laplace transform of this function. To do that, I'm going to need to use partial fractions. If we can find the inverse Laplace transform of this function, which is, say, if we can find the inverse Laplace transform of plus 2 over s squared plus 1, we just divide by t and we're done. So this function I want to write in partial fractions. This should be revision for you from your first year calculus, but let me explain the method. I have an s and an s squared plus 1 on the bottom. I want to write this as something over s plus something over s squared plus 1. And what is the something on the top? The something on the top is always a polynomial of degree 1 less than the function on the bottom. S, for example, is a first degree polynomial, so on the top, just a number. S squared plus 1 is a second degree polynomial, so on the top, there should be a first degree polynomial. I want to write this as some number a divided by s plus some number bs plus some number c divided by s squared plus 1. Put everything over the same denominator, and then rearrange. This is the same as a plus b s squared plus cs plus a divided by s squared plus 1. And all of this thing on the top must be equal to 2. A must be 2. CS must be the same as 0s. And a plus b s squared must be the same as 0 s squared. So a is 2, b is minus 2, and c is 0. Okay, so in partial fractions, our function is 2 divided by s minus 2s over s squared plus 1. We need the inverse Laplace transform of this function. And what we do is we pick up our table of elementary Laplace transforms, and we're looking for something which looks like 2 divided by s, but perhaps with different numbers. Here it is. And we also need something which looks like 2s divided by s squared plus 1. Here it is. These are the elementary Laplace transforms that we're going to need. The Laplace transform 1 is 1 over s, and the Laplace transform cos at is s over s squared plus a squared. I'm going to write these at the bottom. Now that we know which ones we're going to use, we know how to split up our function. We know to split this up as 2 multiplied by the inverse Laplace transform of 1 over s minus 2 multiplied by the inverse Laplace transform of s over s squared plus 1, which of course is just 2 minus 2 cos t. Almost finished. Just divide by t, and we found our f of t. why are we studying the Laplace transform in our differential equations course? Because we can use the Laplace transform to solve initial value problems. And the key formula is that the Laplace transform of f prime is equal to s multiplied by the Laplace transform of f minus f of 0. There's also a formula for the second derivative. The Laplace transform of f double prime is s squared multiplied by the Laplace transform of f minus sf at 0 minus f prime at 0. And we have a formula for f cubed. The idea is the same. Look, 3 derivatives just here. So we start s cubed multiplied by the Laplace transform of f, and then it goes s squared, s, and then just 1. And then f at 0, f prime at 0, f double prime at 0. There's a pattern here. And we have a formula for the nth derivative of capital F. The pattern is the same. The nth derivative, it starts s to the power n multiplied by the Laplace transform of f, and then the powers of s decreases, s to the n minus 1, s to the power n minus 2, etc. And these are multiplied by f at 0, f prime at 0, f double prime at 0, etc., etc. Because these are very important formulae, I'm going to prove them. And again, I'm going to be using integration by parts to prove these. So, the Laplace transform f prime, that's the integral of e to the power minus st f prime. This green function I'm going to call u, and the orange function I'm going to call v prime. By integration by parts, that's just uv, e to the power st, f of t, and then minus u prime v, or minus the derivative of e to the power minus st, ft. Okay. Now, I'm not doing the limits here. Of course, when we do integrals from 0 to infinity, really it means the limit as r tends to infinity, etc., etc. I'm being lazy and I'm not writing all those details here. Just understand, anytime I write an integral from 0 to infinity or calculating a function at 0 and infinity, really I'm thinking in terms of limits. The limit as r tends to infinity of e to the power minus st is 0. So the first term will just be 0. Replacing t by 0, e to the power 0 is 1, so we just get f of 0 here. And then minus the integral from 0 to infinity, minus s e to the power minus st f of t. That's the same as minus f of 0 plus now s. S in terms of the integral is a constant, so the s can come out. Integral from 0 to infinity, e to the power minus st f of t dt. But what have I written in red? This is just the Laplace transform of f. So we just get minus f at 0 plus s Laplace transform of f. And that is the formula in part 1. All I've done here is I've done integration by parts. Now I want to prove the formula for the second derivative of f. And I'm going to use the first formula, the formula I've just proved. But every time I see an f, I'm going to replace it by f prime. So instead of the Laplace transform f prime, it's going to be f prime prime is equal to s. Instead of Laplace transform f, it's Laplace transform f prime. And then instead of minus f of 0, it's minus f prime of 0. We know that's true, but we also have a formula for the Laplace transform of f prime, because we've just done it. So we just have s squared Laplace transform of f minus s of f0 minus f prime of 0, which is what we wanted. Parts 3 and parts 4 I'm going to leave for you to prove. Just use part 1 again, however many times you need. Now, solve y double prime minus y prime minus 2y is equal to 0 with the initial conditions y of 0 is 1, y prime of 0 is 0. We know how to solve this from chapter 3. We could solve this in terms of using the characteristic equation. We find that the roots are minus 1 and 2. So the general solution to the differential equation is constant e to the power minus t plus constant e to the power 2t. And then we can use the initial conditions to find c1 and c2. So the answer to this problem will be 2 over 3 e to the power minus t plus 1 over 3 e to the power 2t. But this chapter is about the Laplace transform. I want to solve this problem again, but using the Laplace transform. Well, this time we have an easy differential equation, but let's suppose we don't. Let's suppose we had a more complicated equation that we couldn't do the previous methods. How could we solve a difficult differential equation? One way is to use the Laplace transform, because the Laplace transform eats derivatives. Using the Laplace transform, instead of a difficult differential equation, we might end up with an easier equation for capital Y. Solve the easy equation to find capital Y, and then take the inverse Laplace transform to find small y. That's the idea. So, what do? We start with our differential equation, and we take the Laplace transform of this. The Laplace transform of the left side is equal to the Laplace transform of the right side. Because the Laplace transform is a linear operator, on the left we have the Laplace transform of y double prime minus the Laplace transform of y prime minus 2 times the Laplace transform of y. And again, because we have a linear operator always maps 0 to 0. So on the right side, we just have 0. And remember, we have these formulae for the derivatives. We know that the Laplace transform of y double prime is s squared capital Y minus s at y0 minus y prime at 0. We can use that here. And we also know that the Laplace transform of y prime is s capital Y minus y0. We can use that just here. So we have s squared capital Y minus s at y0 minus y prime at 0 minus in brackets s at capital Y minus y at 0 minus 2 times capital Y is equal to 0. Now, y prime at 0 was equal to 0, and y at 0 was equal to 1. Rearrange, we have s squared minus s minus 2 capital Y plus 1 minus s. Which we can solve for capital Y and find that capital Y is s minus 1 divided by s squared minus s minus 2, or s minus 1 divided by s minus 2, s plus 1. I need to use partial fractions again. I'm going to skip the details here. I'll leave this for you to double check. I think I get 1 over 3 multiplied by 1 over s minus 2 plus 2 over 3 multiplied by 1 over s plus 1. And then we can take the inverse Laplace transform. Remember that the Laplace transform of e to the power 2t is 1 over s minus 2, and the Laplace transform of e to the power minus t is 1 over s plus 1. So we know that small y must be 1 over 3 e to the power 2t plus 2 over 3 e to the power minus t. Which of course was the same answer that we found using the previous method. Let's do another example. Solve y double prime plus y is equal to sine 2t with the initial conditions y of 0 is equal to 2, y prime of 0 is equal to 1. We're going to take the Laplace transform of the differential equation. We're going to use our formulae for the Laplace transform of the second derivatives of y. We're going to put in the initial conditions and rearrange, and we'll find a formula for capital Y. So we start with the differential equation, and we take the Laplace transform of everything. We use our formulae. Instead of the Laplace transform of y double prime, we write s squared capital Y minus s y at 0 minus y prime at 0. Instead of the Laplace transform of small y, we just have capital Y. Instead of the Laplace transform of sine 2t, we have 2 over s squared plus 4. We can put in the initial conditions because y of 0 is 2 and y prime of 0 is equal to 1. So there we go. We can rearrange to solve for capital Y. So capital Y will be 2s plus 1 divided by s squared plus 1 plus 2 over s squared plus 1, s squared plus 4. We need to use partial fractions on the second term. It's going to be something over s squared plus 1 plus something over s squared plus 4, where each one of these somethings is a first degree polynomial. I'll leave this for you to check. I think we get 2 over 3 and minus 2 over 3. Let's rearrange some more. Now, what I'm going to do is I'm going to take this plus 1 and I'm going to join it together with this 2/3 to get 5/3. So then the first term is 2s on the top, second term is 5 over 3 on the top, and the third term is 2 over 3 on the top. Then I look at my table of elementary Laplace transforms and I try to find things which look like these. On my table of elementary Laplace transforms, I find an s over s squared plus 1, so I know I can take the factor of 2 out. I also find a 1 over s squared plus 1, so I take my 5 over 3 out. I don't find 1 divided by s squared plus 4 on my table, but I do find 2 over s squared plus 4. So instead of taking a factor of 2/3 out, I just take a factor of 1/3 out. Because then I have 2 multiplied by the Laplace transform cos t plus 5 over 3 multiplied by the Laplace transform sin t minus 1/3 multiplied by the Laplace transform sin 2t. And as soon as I know this, I can write down small y. Another example. This time a fourth order linear differential equation. 4 derivatives of y minus y is equal to 0 with the initial conditions y of 0, 0, y prime of 0 is 1, y double prime of 0 is 0, y triple prime of 0 is 0. We start with the Laplace transform of the differential equation. And we use our formula for the Laplace transform of the fourth derivative of y. Here we are. Because it's the fourth derivative, we start with s to the power 4, capital Y, and then it goes s cubed, s squared, s, and 1. And then we increase the derivatives of y at 0. So y at 0, y prime at 0, y double prime at 0, y triple prime at 0. Most of these are 0, remember. This is 0, this one is 0, and this one is 0. So we just get s to the power 4 capital Y minus s squared minus capital Y, or s to the power 4 minus 1 capital Y minus s squared. We're going to rearrange this to find a formula for capital Y, and then we're going to take the inverse Laplace transform to find small y. We have that capital Y is s squared over s to the power 4 minus 1. And we need to use partial fractions, because the bottom is the same as s squared minus 1. The bottom is s squared minus 1, s squared plus 1. We use partial fractions on this, and I'll leave this for you to check. We get a half over s squared minus 1 plus a half over s squared plus 1. So small y is a half inverse Laplace transform of 1 over s squared minus 1 plus a half inverse Laplace transform 1 over s squared plus 1. Look these up on our table of Laplace transforms, and we find that we have a half sine t plus a half sine t. And I can show you a graph of this function. And that is the end of today's lesson. Next time, which is next Thursday, we will continue talking about the Laplace transforms. We'll solve some more initial value problems, and then we'll start talking about step functions. Are there any questions?